the presentation. So, our work addresses critical challenges in aerial surveillance and threat detection, emphasizing the need for advanced, accurate, and real time systems. In an era marked by significant advancements in aerial technology, the positive strides are undeniable. However, these advancements also bring forth the negative aspects, including threats and risk to national security. Therefore, the imperative of having a robust and advanced threat detection system cannot be overstated. Aligned with this imperative, our work leverages the cutting edge YOLO V8 model for real time object detection and segmentation, ensuring high accuracy and confidence. By addressing the deficiencies of the existing systems, which are a lot of time consuming and inefficient, our efforts propel us towards a more secure future. Now comes the objectives. Our research had four primary objectives. First, to develop a deep learning model based on YOLO V8 for efficient aerial object detection and classification. Second, to optimize the model's accuracy for real-time performance. And third, to enhance the model's generalizability for detecting objects of varying sizes. And fourth and the last, to improve its robustness against environmental factors like weather and lighting conditions. Coming to the literature survey part, these are some of the papers which we analyzed, and these papers did some awesome work in YOLO V8 applications. We can see that some of the works have performed real-time flying object detection with YOLO V8 and achieved significant MEP, highlighting the potential of this model in aerial surveillance. We also reviewed other relevant studies to build a solid foundation for our research. Now comes the methodology. Our methodology involved a structured approach. The first part, as in any machine learning or deep learning project, is data collection. So, the data used in this project or in the paper is the part of a competition by AI crowd. And in addition to that, for ensuring variety of images was scraped also from the internet using the Pi Google image library. The next part involved data annotation and labeling. As our data was unlabeled, all the images were manually labeled through the Label Me tool. And after that comes the data pre-processing part, which included the application of Sobel edge detection on the image and enhancement of the edges, followed by training of the model and testing on various videos for analyzing the results and generalization capability of the model. Now let's delve into the YOLO V8 architecture and the results we obtained. YOLO V8 introduces pivotal upgrades for enhanced performance as compared to its previous versions. Mosaic data augmentation, inspired by YOLO V4, enriches context with augmentation concluding in the final 10 training epochs for efficiency. The architecture contains anchor-free detection, which accelerates non-max suppression, reducing bounding box prediction for better generalization. The backbone adopts a C2F module, concatenating the bottleneck module output, speeding up training and bolstering the gradient flow. The decoupled head separates classification and regression task, mitigating loss misalignment through a task alignment score. The comprehensive loss function employs BCE, the binary cross entropy loss, CIOU, the complete intersection over union, and DFL, the distributed focal loss. BCE measures label discrepancies, CIOU assesses the bounding box relations, and DFL optimizes the boundary distribution, prioritizing misclassifications as false negatives. Our dataset had a total of 10,009 images, which had two classes, namely airplane and helicopter, and the numbers were 5004 and 5005, respectively. Now comes the result part. To enhance our model's performance and achieve better generalization capability, we conducted three training rounds. During these rounds, we systematically adjusted batch sizes and incorporated diverse images with varying object sizes, ranging from small to large. This approach aimed to optimize the model's ability to accurately detect objects across a broad spectrum of scenarios, resulting in a more robust and generalized mapping capability. In training round one, we had a little lower MAP and the model was not able to generalize well as well. But in the training round three, we incorporated or included the images which had smaller objects as well as the larger objects and it enhanced the model's MAP and also its generalization capability as well. And the model was able to perform well on even on the data which was not part of the training data set. Now, these are some of the graphs, and these graphs represent the training and validation loss that decreases as the number of epochs increases. These are some figures that represent precision and recall curve for the box and the mask. These graphs are useful in determining how well the false negatives and the false positives are handled by the model. This figure shows a high accuracy confusion matrix at 100 epochs, yet there is a minor misclassification issue. The helicopter is occasionally mistaken for the background. So to conclude, our exploration with YOLO V8 for aerial object detection has been promising. We achieved a strong mean average precision, or the MAP, and high confidence scores, indicating the effectiveness of our model. Furthermore, the pre-processing techniques and model training strategies we employed significantly enhanced the model's precision and accuracy. However, there is scope for further testing and improvement, especially in varying climatic conditions with an expanded dataset with more images. Thanks a lot for giving me this opportunity.